Okay, deductive reasoning. If you'll recall from inductive reasoning that just one counterexample is enough to disprove a conjecture. And so this kind of gives us a problem. If we can't come up with a counterexample, how can we prove that a conjecture is true for every case? Well, that's where deductive reasoning comes into this. Sometimes if we can't prove it by inductive reasoning, then we have to use deductive reasoning, which is the process of using logic to draw conclusions from given facts, definitions, and properties. I like to compare this to, if you ever watched any of these crime shows, you have what's called circumstantial evidence, which means that they can't tie the person there directly, but they've come up with a lot of things that seem to point to that person being the guilty party. That's inductive reasoning. Inductive reasoning uses specific cases and observations to form conclusions about general ones. So it's starting from the specific and going to the general. Deductive reasoning goes the other direction. It uses facts about general cases to form conclusions about specifics. So it starts with the general and it moves to the specific. And that's what we get closely related to what they use, like called direct evidence in the criminal, the crime shows. So let's decide whether this is inductive or deductive. So police arrest a person for robbery when they find him in possession of stolen merchandise. So is this inductive or deductive? Well, this is inductive because, somebody could have planted it on him. He could have just happened to find it. There's no way to directly tie him to that material. Well, gunpowder residue tests show that a suspect had fired a gun recently. Well, this is deductive reasoning because this is an actual, scientific test that finds gunpowder residue. So it's a kind of a specific chemical type of test. Now, to review, we talked about with the conditional statements that conjectures are phrased as if P then Q, which again we also write as P arrow Q, which means we read as if P then Q. And so there's two specific laws of deductive reasoning that we're going to talk about here. The first is called the Law of Detachment. And it seems kind of obvious, but this is one that people can be sneaky with and misuse it a lot of the time. So the Law of Detachment says that if P then Q, if that is a true statement, and if P is true, then Q is true. Okay? So let's look at these conjectures. So we're given that if a student passes his classes, the student is eligible to play sports. That's my basic conjecture. Okay? Now, Ramon passed his classes. So my conjecture is that Ramon is eligible to play sports. This is valid, okay, because Ramon passed his classes matches up with the student passes his classes. And so Ramon is eligible to play sports matches up with the student is eligible to play sports. Let's look at another one. If you are tardy 3 times, you must go to detention. Shayla is in detention. Conjecture, Shayla was tardy at least 3 times. This is not valid. Now notice the difference here. This time we've got Shayla is in detention is being matched up with the conclusion. And our conjecture is the hypothesis. And we can't do it that way. The Law of Detachment says that we have to match the conclusion with the conclusion. So you kind of have to be a little bit to make sure you're matching up what you should be matching up. The next one we want to talk about is called the Law of Syllogism. This was actually really a fun one to play with. And it starts off saying that if P then Q and if Q then R are true statements, then if P then R is a true statement. This is basically how you can set up kind of a chain of conjectures. And it leads to some kind of funny stuff if you kind of take it to the extremes here. But simple examples here is if a number is divisible by 4, then it is divisible by 2. If a number is even, then it is divisible by 2. And so our conjecture is if a number is divisible by 4, then it is even. Okay? Now, the easiest way to do law of syllogism is to go ahead and assign P, Q, and R to your phrases, because otherwise it gets all lost in the shuffle here. So we're going to let P stand for a number is divisible by 4. That's the hypothesis. That's the hypothesis here of my first conditional here. And then I'm going to have a number is divisible by 2. I'm going to let Q stand for that. And so that's going to be my conclusion of my first conditional. Okay? And then R is going to be a number is even. That's the third kind of phrase that I've got going on here. So now that we've got symbols here, let's go ahead and write out what the symbols are saying from my statement. This is saying that if P then Q, so if a number is divisible by 4, then it is divisible by 2. Okay, that's the first part. And then it goes, if R then Q. So if a number is even, then it is divisible by 2. Okay? Therefore, if P then R. Now notice that this does not follow the same pattern that we saw up here. Okay? It's kind of got things a little bit backwards. So this is not valid. Okay, it doesn't follow the right patterning. Okay? So here's another one. Given if an animal is a mammal, then it has hair. If an animal is a dog, then it is a mammal. Conjecture, if an animal is a dog, then it has hair. Okay, so again, let's match up what we've got here. So we're going to have, let P be an animal is a mammal, Q is it has hair, R is an animal is a dog. Okay, so let's write out the way this thing is on the statements. So I've got if P then Q, if R then P, therefore if R then Q. Now this doesn't look like what we had a minute ago, but let's see if we can rearrange some things and maybe make it work. Because what I notice if I flip these two things, I end up with if R then P and if P then Q, therefore if R then Q. See, I've still got it may not be the chain that I had set up before, but I've still got this little chain thing going. If you can set it up so that the conclusion of one statement is the same as the hypothesis of the next statement, then you've got a nice little chain going. Okay, that's kind of how syllogisms need to work. If they don't match up like that, then you do not have a valid syllogism. Okay, shifting gears a little bit here. Looking at biconditional statements. Now, a biconditional statement is a statement whose conditional and converse are both true. Now, if you remember, the converse was where we took the P and the Q and we flipped them. So the converse was if Q then P. And the way we write this is we say this, P if and only if Q. Okay, so we put this if and only if in the middle. We get rid of the if and the then. And we have this new kind of construction here. And we'll sometimes write it because, again, in math we're lazy. So we'll put P-I-F-F-Q. Now that's not a misspelling of if. It's basically saying if and only if. And then another way we'll denote this is we'll put a double-headed arrow. So instead of the single arrow, we'll have a double-headed arrow, and that also means if and only if. So the way that we take a biconditional and we write the converse and the conditional from it is we realize, okay, this is what this is made up of. We've got the hypothesis, we've got the conclusion, and then all we have to do is just put them in the right order. So if I've got a biconditional, two lines are parallel, if and only if, they never intersect. My hypothesis is two lines are parallel. My conclusion is they never intersect. So now I just put together my P and Q part. So if P then Q, if two lines are parallel, then they never intersect. And now my if Q then P, if two lines never intersect, then they are parallel. Okay? So here's another example. So we've got a biconditional statement. A solution is a base if and only if it has a pH greater than 7. All right, so to write the conditional and converse, again, we're going to identify our hypothesis and conclusion and then put our ifs and thens in the right places. So the conditional is if a solution is a base, then it has a pH greater than 7. And then our converse is if a solution has a pH greater than 7, then it is a base. Okay. Now, writing a biconditional statement is kind of basically doing the same idea. You identify your hypothesis and conclusion, you write your hypothesis, put the words if and only if, and then you put the conclusion. So again, the word then is not in a biconditional statement. So if I have this statement here, if 4x plus 3 equals 11, then x equals 2. Okay, I'm going to turn that into a biconditional. So my hypothesis is 4x plus 3 equals 11. My conclusion is x equals 2. So so we put the hypothesis. Let's write the converse first, sorry. So if x equals 2, then 4x plus 3 equals 11. Then to write the biconditional, I put the hypothesis, if and only if, and my conclusion. So 4x plus 3 equals 11, if and only if x equals 2. Now if my biconditional is going to be true, that means that both the conditional and the converse must be true. If one of them is false, then it doesn't work. So let's determine if this biconditional is true, or if it's false, we'll go ahead and give a counterexample. So here's my biconditional. A quadrilateral is a square if and only if it has 4 right angles. Well, my conditional is if a quadrilateral is a square, then it has 4 right angles. Well, we know that's true, so that's no problem. Now let's look at the converse. If a quadrilateral has 4 right angles, then it is a square. That's false, okay? It could be a rectangle. So that statement, a quadrilateral is a square, if and only if it has 4 right angles, we cannot write that as a biconditional because the converse is not true. Now it turns out that essentially any definition we have in geometry, we can write that as a biconditional. So if I've got the definition, a rectangle is a quadrilateral with 4 right angles, I can rewrite that as a quadrilateral is a rectangle if and only if it has 4 right angles. It's tempting to say a rectangle is a quadrilateral if and only if it has 4 right angles, but it doesn't really quite make sense if you see it that way. Okay, then we have congruent angles or angles that have the same measure. Well, we can turn that into angles are congruent angles if and only if they have the same measure. So again, make sure you put your summaries on Objective 6. Go back through and make any notes based on the work that we did in class. And also make sure that you have done your test corrections because they are due next class. And I will talk to you later.